Okay, today we're going to talk about MHD waves. We're going to finish that up, and we'll talk about sunspots. We'll talk about reconnection. Let's see. A couple people are out. That's right.
They're not coming today.
Yeah, that's right. Some are people that anyway. You take this and go way over there to the other side of it. I did this first in a demo. I didn't know what was going to actually happen. I was doing a Saturday morning physics outreach thing. Oh, I actually have a policy of not putting you guys on the film, so I will edit that bit out. So this isn't going to be on the video, sorry. Just because, I don't know. So watch this. Now you hold really still. Now let me do that again. Just make it a little tighter. And I had a kid go clear across, you've been in 101, right? I had a kid go clear across 101. And when you have it, and I had it stretched just right, so that. So can you see that pulse? Now if we let it shorter, then that'll go away. But if you watch it, there's this one beautiful transverse pulse. If I get it a little shorter, then the pulse will travel slower. Why? Why does it go slower when I get closer? Now if I'm here, now this one is really slow. I go way over here. Wave gets faster. So why does it get faster when I move?
It must take the same amount of time.
Interesting argument. Tension goes up because I go away. The tension in the string goes up because of Hooke's law, right? F equals kx. So the tension goes up. So the restoring force goes up, but the mass stays the same. And wave speeds or frequencies are always, when you have some kind of oscillator, the frequency is always the restoring force divided by the mass, square root of that. So if you have a spring, then you have some kind of, then the frequency is like K over mass. For one of these, it's the tension over the mass density. For now, Nalphane wave, it's the magnetic field strength divided by the mass density. Square of the magnetic field strength divided by the square divided by the density. But so this is a really nice example of how an Nalphane wave behaves. So you have a field, you have a magnetic field, that's the analogy of the spring, and it has some tension in it, and when you perturb it transversely, then there's a transverse wave, and the velocity is transverse to the spring. So it travels in that direction. So K is along the spring, V is transverse to the spring. Make sense? So I'll draw this diagram again, but I have it up there. B is in blue there. K in what we just did, K is along B, and V is perpendicular to B. Let's see. This bit, this is almost entirely tangential, but so why does this make a noise like chew? Why does the frequency drop? Well, that's the best. It's really best if you can get the whole thing like it's stretched out really far. So anyway, so why does it make a shooting noise? Because there's several waves that are traveling down here. There's a slinky wave from the stretching of the spring. There's a wave that goes along the coil itself. So there's several waves that are going on, and I can't. If I were smarter, I would be able to say this one is this. But they travel at different. But the wave is dispersive. So different frequencies travel at different speeds because this thing has some thickness. So when you have a thickness, it's got a longitudinal wave that's going to go along the spring and a transverse wave that's going to go sideways. And those are all going to behave differently depending on the wavelength. So you see this thing has a characteristic thickness, right? So waves that are short are going to travel differently than waves that are long compared to the thickness of the wire. Similarly, the size of the wire. So there's some complex dispersion relation that determines how the wave speed changes with frequency. And that's why you hear it starts off high, because those waves travel down and bounce back up to my impedance matching device fast, and the slower waves come up later. So you hear the pitch drop because of the dispersion of the waves in the medium. This is a pretty fun thing. I could play with it kind of all day. I have this other thing, since we're in demo mode. I'm talking about things. This is really a demonstration of Vulture's theorem, which I'm going to make you read about, but not actually talk about in class, because I'm actually running super out of time.
Is it a Torflux?
Is that what it's called?
Yeah.
So this is a coil of wire, and it's coiled in this way that it likes to hang around this size, but there's a lower energy state that's this bigger thing that is, it would rather be here. Like, it will hang around in this lower energy state, but this is a local minimum of energy. This is a global minimum of energy, because this is where it would rather be. I kick it a little bit and it falls into this lower energy state. Why is this one lower energy than this one? It's hard to see. This is a little bigger. This radius is a little bit bigger than this radius, which means the tension forces are smaller, because the tension forces go like B dot grad B. Okay, I totally am now just using this as an analogy. So B dot grad B, when the gradient term is now, maybe it's T dot grad T, where T is the tension vector for this dude. When the gradient is lower, then the total tension term goes down. So if the curvature is higher, then the gradient is lower. If the radius is larger, then the curvature is lower. It's flatter. So that's a lower energy state. Also, this one is kind of stuck here because it's got some helicity. So I'm not going to talk much about the magnetic helicity, but A is the magnetic vector potential, which you'll learn about when you do E&M. And A dot B is the helicity. And this has some non-zero helicity, which means it's going to stay here. So this is the bottom of its potential well, because this is where it can't get to a lower energy state with this than this unless we change the helicity. So I can cut it and make a straight line, and that's going to be even lower energy. But this one is stuck here because of the helicity in the winding. And what that really is there's a winding this way, but there's also a wrapping this way, so that it's like a helix. So you call this a toroflux?
Torflux, yes.
Because I need to be able to source these, because this one's going to break someday, and I need to be able to get another one. But I found this at Walmart randomly. My dad came home one Thanksgiving with a whole pile of these, and we just spent the entire time playing with them, just anyway. So, but it's a useful thing. I'm going to talk about dynamos too in a second. We'll talk about toroidal and poloidal magnetic fields. This is largely poloidal. It's going along the pole, whereas a toroidal field goes around the edge like a torus, like a donut. And I'll talk about toroidal and poloidal when I get to dynamos. Okay, those are my giant springs. Where's my notes for what I was going to talk about today? Okay, all right. So I'm going to talk more about MHD waves. Did I leave them upstairs? No. I just didn't put them where they're supposed to be. So MHD waves. So I went through the derivation of Alfvén waves last time, and I'm going to talk about them again by way of this diagram. I'm going to point to that, but I'm going to draw it again. So I have my universe where this is X, this is Y, and this is Z. Now, without loss of generality, this is a fun phrase that means I'm going to make this simplification, but it's not actually a simplification. It only makes things easier to prove. It's not actually making the system any simpler. So if I've got a magnetic field, my last chart of blue, that's in this direction, and we'll put the wave vector in the xy plane, because I got to put it somewhere, and I might as well just rotate it so that it's in that plane. So this is the direction of the propagation, and this is the direction of the magnetic field. And then the velocity can be one of two things. Either it can be perpendicular to the plane, or it can be in the plane. Now, we did the version where it's perpendicular to the plane, and when you do that, so the dispersion relationship we got, so we started off with continuity, Euler with the Lorentz term, the Lorentz force is the curl B cross B term, and the induction equation, which gives you the magnetic field growth. We pack all those things together, and we got a dispersion relation that was kind of gnarly, that I'm not going to talk about, I'm not going to write up again, because I'm just going to write the result that I want. If we take that long dispersion relation and assume that V is perpendicular to K and B, then we have that V dot K equals V dot VA equals 0. And remember, VA is a vector. It's B over the square root of 4 pi rho. Now, if you're in CGS, this isn't a 4 pi, it's a mu naught. But it's basically B over square root of rho. Those are the important bits. So the Alfvén speed is a proxy for the magnetic field, but it also has this density in it. Now, density is constant for everything that we're doing, so I can just use whichever. So if we make this assumption, then the dispersion relation simplifies to this nice relation, omega squared equals K dot VA squared. So what does this really mean? This means that if I have, say I filled the room with springs, and they're all going in one direction, and I flick all of them at once, if I perturb it in that direction, perpendicular to the field, then the wave will travel in that way. But if I perturb it a little bit differently, then I can get the wave to not travel along the magnetic field, but I can make it travel oblique to the magnetic field at an angle. So I can make a wave that's traveling in that direction, even though the field is in that direction. But this dot product means that that wave travels slower. So if I were to draw okay, this is a radial plot so R here is the actual phase speed, and theta is going to be K dot VA, and theta is the angle between K and VA. So theta opens up this way. So omega squared is K dot VA. So when theta is 0, that means I'm here. I'm going to be at some distance, and this is going to be VA. As theta increases, this goes like cosine, and this goes like, so that when you're at 90, it's 0. And then it goes this way as you keep going, because it's negative. So this is what the velocity looks like as a function of angle. So if you're pointing in this direction, if you're pointing along the magnetic field, then the velocity is maximal and it's VA. If you're pointing oblique to the magnetic field, the velocity goes down until you're orthogonal to the magnetic field. You can't have an Alfvén wave traveling orthogonal to the magnetic field because it doesn't support that. It won't do it because it's in the tension, and the tension makes it want to go that direction. Now, if I have a disturbance that's going orthogonal to the magnetic field, then I need a different wave. So this is Alfvén waves. So Alfvén waves we're going to write this up here so that we got all of this. Here, I'll do it this way. So it stay on here. So the Alfvén wave is the transverse wave. It's incompressible. It's incompressible because we decided that K dot V equals 0. Why is this equivalent to incompressible? What does incompressible mean? Incompressible means 0 dt equals 0. It also means div v equals 0. This is just div v. Remember? Because remember, the k's all came from spatial derivatives. So k and spatial derivatives should be tied together in your head. You can also tie that to momentum in your head just to plan ahead for quantum mechanics. But k is a spatial derivative, so k dot v equals 0 means div v equals 0. So the Alfvén wave is an incompressible wave. It's transverse. V is perpendicular to k and b, and it travels with a phase speed v phase equals VA dot K. Anything else I need to say there? I might have other things to say in a second. So let's now, the book doesn't do this, but I do it because I like compressible fluid dynamics. And so I'm going to talk about the other waves. So what do the other waves look like? So now we're going to assume that velocity is in the plane made by V and B. And if it's at some angle, we'll just use some admixture. I'll show you why that works in a second. So now there's a number of different ways you can solve these equations to get at the properties of the non-Alfvén waves, the other two waves. I'm going to do it this way because I don't know, I like this way. So we take our equations and we linearize them. Do I have the linearized equations up there? No, I have the full equations up there. So we have continuity, Euler with the Lorentz force. I guess this is the MHD equation. This equation doesn't really have a name. Maybe Tully has it, or somebody like that. And we have the induction equation, which induces magnetic fields from velocities. So we take those guys and we linearize them. And when we linearize them, we're left with d by dt of rho 1. So, okay, rho equals rho naught plus rho 1, etc. d by dt of rho 1 plus rho naught d by d, no, not yet. Div v equals 0, div v1 equals 0. Let's write that as a vector. We're left with d by dt of v1 equals minus c squared. Let's put a rho naught here. minus c squared del rho, no, grad rho, minus del cross B1 cross B naught. So this is the linearized Lorentz force. So del cross B1 is the fluctuating current, and B naught is the mean B. And then the induction equation looks like d by dt of B1 equals del cross B1 cross B naught. So I did this last time. It's also in the text, so you don't necessarily need to write these down unless you're unless that's how you take notes, which is how I work. So we have our linearized equations. I'm going to rewrite this slightly. I'm going to draw a slightly different picture. The reason I'm changing bases is just to make things interesting, but also it's the way I did it. So if instead now, same coordinate system, x, y, z, but now I'm lining my wave vector up with x. My magnetic field is now in the xy plane, and then the velocity is again either perpendicular to that plane or in that plane. And now k is along x. The reason I do that is now all my derivatives are x derivatives, because the other k's went away. So now I only have derivatives along x. And b does not have a z component. This will matter in a second. So I'm going to take these equations and I'm going to rewrite them slightly. So let me tell you what I'm going to do real fast. So basically I'm going to take this set of equations and we're going to turn it into a matrix. We're going to define some vector q, which is equal to rho vx, rho vy, rho vz, hx. Okay, I'm changing it to h from b just because that's the way I did it in my notes. H and b are related. Most of the time I'm in a vacuum, so they're the same. Hx, hy, hz. So this is q. This is my vector of unknowns. Right? Okay, this is a vector too, so I've got a vector that contains two vectors. That doesn't really matter. I just made one new vector. So we're going to rewrite this as a matrix equation. So we've got A times Q equals Cn times Q. Now A is a matrix, Q is a vector, Cn is a wave speed. So how many of you have taken linear algebra? A couple of you, but not all of you. Okay, so you guys have not found eigenvectors of eigenvalues of matrices yet, is that right? Yes, I have seen eigenvalues.
Oh yeah, in quantum.
Okay, so you did in quantum. So this is an eigenvalue problem. I got a matrix times a vector is equal to some number times that vector again. Why do I want to do that? Well, because then I can diagonalize it. I'm not going to do this, but one can, and it is a useful thing to do. You can then diagonalize this matrix. And then, so this is 7 equations. I only wrote 3, but there's three components to this one and 2 components to this one. Why only 2? I'll explain that in a second. So this is 6 equations. There's a pressure equation too that you might need. But this gets us what we need. So this is 6 equations, which gives me 3 waves in 2 directions. So if I've got 6 equations, that's going to give me a 6 by 6 matrix here, and that's going to give me 6 eigenvalues and 6 eigenvectors. But the eigenvalues and eigenvectors are only different by a sign. So there's only 3 eigenvectors that we need to worry about. Let's see, do I need to go through setting that up? Do you want me to turn this into a matrix? Is that useful to see? Here, pedagogically, I'm not sure if that's worth doing. Let's do it anyway. So you over there, and you on my list of stuff that I want to talk about. this one, which has some stuff in it already. Point the camera. Let's just do this real fast because it's not super painful. So let's start with a continuity. So d by dt of rho 1 plus rho naught d by dx of v1. Now, this is a divergence. So this is just the x component of v1. Because I aligned my k vector with the x-axis, so the other two derivatives go away. Equals 0. I'm going to rewrite dt and dx as a delta t and a delta x. And then I'm going to this is 1 over dt and this is 1 over dx. So I'm going to multiply through by delta x, and then this turns into a sound speed. So this is a speed times rho 1 plus d by rho naught d, the d by dx goes away. Now I got a simpler equation. That's just a velocity times my perturbed density plus rho naught v1 equals 0. And I can just go along down my list of equations and write down a similar set of equations. So I have, this equation, this gives me vx, vy, and vz. So I get one for vx. And they all look a little different. Actually, let's spend a minute and talk about that. So d by dt of vx. Okay, now all my velocities are perturbed velocities. There's no mean velocity, so vx is the fluctuating vx. There's no mean, so I'm going to drop the one subscript on velocities. I'll try to leave them on everything else. So d by dt of vx equals minus 1 over rho naught grad rho naught. Oh, let's make this okay, I'm going to use a squared instead of c squared because I've got too many c's. A is now the sound speed. This is very common. A is the sound speed in lots of places. Sometimes I call it C sound. I'm going to call it A right here. Plus the Lorentz force. So now we're looking at the x component of the velocity. What's the Lorentz force look like? Well, it looks like div b squared over 8 pi minus bi bj over 4 pi. So let's rewrite this. This is now d by dj. This is my j component. I component is x, because that's how this equation works. So if I expand this out a little, the only derivative that I'm left with, because of how I've oriented my coordinate system, the only derivative that I get is the x derivative. So this is d by dx of b squared over 8 pi minus bx over 4 pi. So this turns into dx of, sorry, I said I was going to make him h. I'm going to call him b. Here, let's do b. I can do that. Because apparently my hands can't write h here. So when I expand this out, this first term turns into by times d by dx of by. There's no bz because I canceled it by removing the equation, or by orienting my coordinate system. So this term is d by dx of b squared over 2. B squared equals bx squared plus by squared. So when I take d by dx of that one, I'm left with by times d by dy of by. But what's d by dx of bx squared? It is 0. Why? Because div b is 0. So div b is dx bx plus dy by plus dz bz. I've gotten rid of these two, and this equals 0 by Maxwell. I get rid of these two because I oriented my universe so that the derivatives in y and z are 0. So that means the derivative of x along x is also 0, because div b is 0. So if I'm looking at the x momentum, oh, I'm sorry, this should be a row here. If I'm looking at the x momentum, then my Lorentz force has the pressure gradient and the tension term. When I expand that out, those simplify and they become just, this turns into simply by times d by dx of by, and then that other term goes away. So my x momentum equation, I'm going to rewrite it simpler in this other way, simplifies to my wave speed times Vx plus a squared rho 1 plus 1 over 4 pi. 4 pi, not 8 pi, because the 2 comes down from the squared. By delta by. So this is by naught, and this is by1. Let's call it by1. Let's keep our notation consistent. So this is the mean field times the fluctuating field. That's what came out of that. And I keep going with this same process, and I'm left with Cn times Vy plus, okay, on the Vy component, let's look at the what the y momentum looks like. So d by dt, rho naught d by dt of Vy equals minus a squared div p delta ij plus b squared over 8 pi delta ij plus by bj over 4 pi. So this is the, sorry, that's a minus sign. So now I've just written out what the y component is, but since I oriented x along x, then I'm looking at just the y component of this. My derivative is along x, so dj, j equals x. So this term goes away because of the delta function. And I'm left with just the HYHZ term. The longitudinal derivative of b squared also goes away, and I'm left with Cn times Vy minus 1 over 4 pi 8 Bx not b, sorry, Z1 equals 0. So I have a difference, let's just abandon that thought. So I have a difference between my x component and my y component because my x component is going to feel the pressure because that's the divergency parts. My y component is only going to feel the Lorentz force. And then I get its two similar terms. CnVz minus 1 over 4 pi Bx naught By1 equals 0. So the z component depends on the y component of the velocity because of the cross product. And then Cn Vy plus By delta Vx minus Vx delta Vy equals 0. This is the induction equation. So this is just dB dt equals V cross B is this. And then I get another term, CnV by1, bz1 plus that term goes away, and then I'm left with minus bx delta vy equals 0. Okay. What did I do? All I did was I took my linearized equations there. I rewrote them a little bit so that I've got some wave speed times. Now here I've got my vector of unknowns. So this is now Cn times Q, and then this mess of stuff here is some matrix times just Vn again. So you can sort out what the matrix looks like by just drawing a matrix and putting the things in the right spot so that the matrix gives you this. So then I'm left with a thing I got to take an eigenvector of, which isn't super painful, but I'm not going to do it. What you're left with is, so you rewrite this. So we had Cn times Q plus matrix A times Q equals 0. That's what I just wrote down and I erased. This gets you your perturbed equations again. It's also an eigenvalue equation, so we can solve for the eigenvectors. So there are 6 eigenvectors. And they are VA plus or minus VA, because it can go that way or it can go the other way. So I've got 2 waves traveling in either directions. So this is the Alfvén waves. And then I've got Cn equals, okay, this is horrible, A squared plus VA squared over 2 plus or minus the square root of VA squared minus A squared, all that stuff squared, minus 4 times A squared VA squared sine squared of the angle between A and K, or between K and V. This is a much grosser expression. Did I do that right? Oh, I think this is supposed to be the inside here is positive definite. So there's no weird singularities here, so that has to be a plus sign. So what does that mean? So I've got 2 different wave speeds because I got a plus and a minus of this thing. So if this term is gone, then my waves travel at the sum of VA and the sound speed. Because these are waves, so this wave is perpendicular to this way the velocity is perpendicular to the magnetic field and the velocity is perpendicular to K, so it's incompressible. The other 2 waves are compressible, so they've got an acoustic wave component on top of them. So you've got the magnetic disturbance and an acoustic disturbance stacked on top of each other. So there's a sound wave like we did a long time ago, and an Alfvén wave like I did on Tuesday, but they're kind of superimposed on top of each other. And depending on the phase of whether or not the sound wave is making things denser in the right way, the phase of the acoustic and the magnetic waves, if they're in phase, then you get the plus sign and the wave goes really fast. And if they're out of phase, you get the minus sign and the wave goes really slow. So, so our waves are typically ordered. The fast is always the fastest. You can tell that the fast wave is the fastest just by looking at it. It's going to go like VA plus A over 2. And then the Alfvén wave, and then the slow wave. And the only difference between the fast and the slow wave is does the acoustic part of the disturbance make the Alfvén speed higher or not? So, there's a lot of numbers that I only kind of touched on. Oh, but I want that one. So there's 3 waves and 2 groups. There's the Alfvén wave, which is transverse and compressible. And then there's the fast and the slow wave. And these are compressible. And we'll call them magnetoacoustic waves. The velocity is parallel, is in the plane of V and B, K and B. And the phase speed is this complicated thing that I'm not going to rewrite again because it's not. I think the complicated thing is in the book. Okay, does anybody have any questions about fast and slow waves? Everybody good so far? Okay, the last thing I'm going to talk the next thing I'm going to talk about today. So the last thing is reconnection, but I'm probably not getting there. Is magnetic convection. So, come on, man. So we did convection kind of fast. I did Rayleigh-Bernard convection kind of fast because it was like the fifth perturbation stability thing that we had done. But I realized that I could have spent some more time on it. Specifically, there's this thing called the Rayleigh number. And it's equal to alpha, beta, g, d to the fourth over kappa nu. That's awful. Okay, alpha is compressibility, is thermal compressibility. So how much does it shrink? Beta is the temperature gradient. G is gravity, and D is the distance. So what's this setup? Sorry, I should have done that first. I got some fluid in some bucket, and it's got some distance D. There's a hot side and a cold side. It's got some different distance D. The fluid is thermally expansive, so it'll get less dense as you heat it. That's why it floats. There's a temperature gradient, there's gravity, and then we also have the thermal conductivity and the viscosity. So the Rayleigh number tells you whether or not you're going to start convecting. But it also depends on wavelength. So not everything convects the same. So if I make a phase diagram of Rayleigh number versus wave number K, it looks like something like this. And this is unstable, and this is stable. So if I pick a particular size here, say, then from this curve, which you can get somehow, I don't particularly care, get it from simulations or some more elaborate theory. Chandrasekhar probably has an analytic expression for this in one of his fabulous books. So if I pick a K, then there's a critical value of R that depends on K that tells me when I'm going to start convecting. So if I increase the thermal compressibility, then that will raise R and I'm more likely to convect. So I make it expand more when I heat it and it's more likely to convect. If I make the temperature gradient higher, so that's just heat up the bottom, just turn the temperature up on the bottom, more likely to convect. That raises R, raises it, so it's more likely to convect. More gravity, more likely to convect. Bigger thing, more likely to convect. If I increase the thermal conductivity, then I'm less likely to convect because it's not the temperature is just going to go straight through my stuff and not expand anything. If I increase the viscosity, then it's gluier and it can't roll over very well. So the Rayleigh number has a whole bunch of physics packed into it. And we can use it by having this diagram. And there's a minimum. So let's just think about changing beta. So here, beta is just a knob on the temperature underneath my pot, as it were. So this is just the temperature at the bottom. If the temperature is too low, then nothing will convect. So this is like you turn your pot on your stove really, really low, and it won't boil if the pot is low. If the pot is big and the fire is not on very high, then it won't boil. Just think about trying to hold a lighter under a bathtub. Not going to make a convection. But as I increase the size of my lighter, there is a first wave number that will go unstable first. And we call this the critical Rayleigh number. And there's a critical size that comes along with it. This is going to depend on like the size of the bathtub and other boundary conditions. But the physics is still there. There's a critical wave Rayleigh number that is the lowest temperature gradient I can have before the thing starts to convect. So this is all stuff I should have said 3 weeks ago. Now I'm going to add a magnetic field. So how does that look? So now my box has a magnetic field. This is the tiniest little piece of junk. In this direction. What does that do? Magnetic fields do two things. Magnetic fields have tension and they have pressure. And both of these things matter when you're looking at convective stability. So the book gives an example, though you can find examples with all kinds of topologies. The book talks about an example where you just have a vertical magnetic field. So what happens is when I heat the bottom, fluid will start to go up, but it can't turn over. That's suppressed by the tension. So I've got this tension in the magnetic field that's going to resist the bending, so it can't roll over. So the compression is suppressed, or so the convection is suppressed. So I add this magnetic field here, and it acts like rebar in the fluid. It holds it all still, and it can't convect because it can't bend over. So there's this Chandrasekhar number. Chandrasekhar was one of the greatest physicists ever. He's got papers on all kinds of stuff. Notably, black holes and magnetic fields were the things that he did a lot of work in. So the Chandrasekhar number is b squared over lambda. B squared over 4 pi rho naught. B squared and rho almost always show up together. Times d squared over the magnetic diffusivity lambda. So if I make it more conductive or less conductive, then the diffusivity goes up and Q stops. Like then the magnetic field can slip. So what the magnetic field does is it adds this suppression effect and raises this by Q. It raises the critical Rayleigh number by Q. So if I add a magnetic field, then my curve looks like this. And my critical number for convection goes up. So magnetic fields can suppress convection some of the time. Let's leave that up. And I'll talk about magnetic fields making convection. Let's see. All right, camera. Here are our waves. Yeah, so now if I have a situation where I'm going to put the magnetic field, I'm going to use up this chalk right here. They're not supposed to be connected at the end. I just can't pick the chalk up. I'm just going to do this until the chalk is gone. All right, so now I have a tube with a magnetic field in it. But not here and here. Now I've got some thing, and the magnetic field is sideways. That doesn't really make a huge difference, but that's how I drew it. Now, if this thing is in basically hydrostatic equilibrium-ish, then my pressure gradient across this whole thing has got to be 0. So I've got some P inside and some P outside. Magnetic fields make a pressure, and they add to pressure, like B squared over 8 pi. So the pressure in here, P inside plus B squared over 8 pi has got to equal P outside. Now, if we assume that the temperature is constant, then P inside T equals, no, that's not right. Let's not dirt that up too hard. P inside equals rho inside T, and P outside equals rho outside T. And you can see by doing a little bit of algebra that we get that rho inside minus rho outside over rho outside B squared over 4 pi rho outside. We just do a little bit of algebra. And you can see that the pressure, the important bit is the gas pressure in here is lower than the gas pressure outside. You don't need to worry too much about this. Just think about this. And also, the density inside is going to be lower than the density outside. So what does that mean for the stuff in this tube? That means it's going to be buoyant because the density is low. The magnetic field keeps pressure out that doesn't need to be there, so that means it can also keep crap out. So that means my density is lower here, and that means this thing is going to start to float. It's going to start to float in a weird way. I need more blue. So it's not going to be totally uniform. It's going to start to float like this. So there's going to be some bolt that comes up and leaves the surface. And then you're going to be left with, if this is, say, the surface of the sun, as a arbitrary example where this might happen sometimes, I have these magnetic fields that will rise up and then leave the sun. And then we're left with two things. We're left with two footprints where the magnetic field comes out of the sun, and then we're left with this loop over the top of where the magnetic field is. And this is where you get sunspots. You get buoyant instabilities because the magnetic field keeps the density low, it then floats and then it breaks through, and then you have sunspots on the surface. And you can see sunspots always have to come in pairs. They always have to have opposite signs. And you can see this if you look at what the sun is actually doing. That's what it does. So let's do that. Let's look at what the sun is doing. And I forgot to record with the thing I like. So we'll just point the camera at the screen. Come on, wake up. TV, I need you. There you go. So there is a telescope called, there are several telescopes that are pointed at the sun. One is called SDO, the Solar Dynamics Observatory. And this is a satellite that's parked at the L1 Sun Earth Lagrange point. You guys know what the Lagrange points are? No? Okay, so this is quick, so I'll just do that real fast. So when I have two gravitational bodies, the gravitational force falls like 1 over r squared. So if I've got one with m1 and another with m2, then at some r, these two are equal. This is super overly simplistic because it's actually a rotating system. So, You got to take into account the Coriolis force too, but that's not a big deal. But at some point, if I have the sun and the Earth, there's a point in the middle where the gravitational force is balanced. And that's the sum of the gravitational and Coriolis forces, but that's okay, or centrifugal forces, but that's okay. And this is called L1. This is the L1 Lagrange point. It turns out if you do the math, there are 5. There's another one out here that's outside the Earth where everything balances. This is a little counterintuitive. Here, this makes sense. You're getting pulled from both sides. But here, you're getting pulled by the pair, but also swung around by the centrifugal force. So the pulling in and the throwing out balance. So this is L2. L2 is where James Webb is. It's also where Planck was. There are several satellites out at L2. But SDO is at L1. Now the nice bit about L1 is you can put a satellite here and it's basically a stable point. So there's a point in space that you can orbit. It's a point in space that you orbit, but you orbit this point in space, which is totally unsettling to me. But it's a flatness. If you look at what the gravitational potential is doing, there's a flatness to the gravitational potential here. L2 is only kind of stable. It's attracting on this side and this side, but it's repelling on this side and this side, which takes a little bit of gas, which is why James Webb is only going to last for a couple of years, because it needs gas to keep its course correction so that it doesn't fly out. Not a lot, so it's got a lot of fuel, so it'll stick around for a while. So the Solar Dynamics Observatory is at L1. There's another one. Pretend that's round. There's another pair of satellites called Stereo. And there's Stereo A and Stereo B, which one is in an Earth trailing orbit and the other one is an Earth preceding orbit. And they launch from Earth and they're just taking binocular pictures of the sun. So they get this stereo view of the sun from different angles so that you can see the same structure from different angles. Why do you want that? Because this is how you get depth perception. So you can get depth perception by having 2 satellites. It's kind of awesome. So the Solar Dynamics Observatory has a picture of the sun today. So let's look at that. What does the sun look like today? Oh, let's point the camera at the TV. Wake up, TV. Come on, man. I told you to wake up. Let's try it again. Sunspots. Connecting is a good sign. This is boring waiting for my technology to do what I told it to do. Why do you say no signal? There was a signal before. Did it do it? Oh, it did it. Okay, cool. Jesus Christ. Making me look like a boomer. Here is the sun today. Oh no. I wish I could get him to open on that thing. I bet I can. This is what the sun looks like today.
I thought stars weren't green.
Yeah, that's right. So SDO has 13 wave bands that it measures things on. So this is a map of what all and a color map. It's very nicely designed. They color code all of their images, and they're always really consistent. And the different colors are different cameras on the telescope. So the black and white ones are the Dopplergrams and the magnetogram. This is kind of awesome. Which direction is the sun rotating? You can see right here. It is rotating this way. Oh no, it's going this way because black is because of the color map. Because black is towards you and white is away from you. You'll see this in a second. There's a magnetometer that measures the magnetic field strength based on Zeeman splitting. Have you guys done Zeeman splitting in quantum yet?
I recognize the name.
Okay, but you haven't covered it yet. You would know when you would get there, and there's, I don't know. It's not super bad, but you spend a bunch of time with it. So you'll do Zeeman splitting, and basically Zeeman splitting is if I've got a, say, hydrogen atom, there's a degeneracy. So I've got a proton and an electron, and the electron's got some spin. It can be up or down. And it really can't see, okay, there's an interaction between the electron spin and the proton spin, but it's super weak. So for the most part, you can't see it. But if you put a magnetic field, so I have the same energy whether the electron spin is up or down. So I get a degenerate states. But if I put a magnetic field in, then the magnetic field and the electron spin interact, and one direction is lower than the other. So when there's a magnetic field, the magnetic field splits that degeneracy in the levels. Does that make sense? So when I have photons falling from the upper level and the lower level, they have slightly different energies. And that lets me measure the magnetic field strength, because it turns out those two photons are also polarized in opposite directions. So we can measure the magnetic field strength with a magnetometer like this using Zeeman splitting. And black is into the page and white is out. Maybe it's the other way. I can absolutely no way of being able to tell. Then there's several others. I'm going to leave this up just so that we can see what it is. So they're all very specific wavebands targeting very specific physical features in the sun. So this filter at 300 angstroms is the top of the chromosphere. This longer wavelength one at 4,500 angstroms gives you this photosphere. These short ones measure short wavelength photons. Those are high energy processes. So this one at 94 angstroms is millions of degrees of gas. So these are, I think it's an iron line that they target. So this is what the sun looks like right now. So you can see that there's a little magnetic activity going on over here, but it's kind of quiet right now. I wanted to talk about those in a second. Here's what the magnetogram looks like. So there is some activity, and you can see, what do you see from this? Always in pairs, always in pairs, always in pairs. There's always an up and a down, because every one of these is a loop of magnetic field that came out of the sun and goes back into it. These are all pretty quiet. They're not doing anything really violent. And that's the... Oh, this one is nice. Why do they measure the Doppler? So they measure the Doppler shift off the surface of the sun. And you can see that it's rotating because this one side is coming at you and the other side is going away from you. That's not why they measured it. That's not why they measured the Doppler shift. They measure the Doppler shift. You see all the fluctuations. All of these fluctuations of the surface of the sun coming up and down. And you can use those coming ups and downs and what we know about the sun to measure the inside of the sun in a process called helioseismology. They measure the vibrations of the sun to learn what's going on inside. It's one of the coolest. It's one of the coolest things. Okay, so that's today. This, I think these are all the same. Here's one of the larger sunspots that have been observed. And this one, the reason I have this one is this is from late October 2003. And during that time, there was an enormous wildfire in San Diego that basically shut the entire city down for a couple of weeks because the whole fucking thing was on fire. Now, with a wildfire comes a giant blanket of smoke. And this blanket of smoke happened to be thick enough that you could look at the sun and see the sunspots with your naked eye, which I thought I was going nuts when I looked up, and I'm like, well, that's a sunspot. I shouldn't be able to see that. I should be blind, but there is all this smoke. And so I went and looked because the SDO was up, and I was like, yeah, that is in fact the sunspot that I saw. This guy here then erupted a couple of days later with one of the most violent coronal mass ejections that's ever been observed. Let's see. Let's look at some more big ones. This is the largest one that SOHO is, or that SDO has observed. This one is from 2014. This is a blob of magnetic field that's about the size of Jupiter. It's a really goddamn big object. So what does it look like? Let's just, oh no, we got movies of these. These are great. So here, you watch the sun. This is a film of the sun. It doesn't evolve a ton in this one. This is a couple of days. I don't remember exactly how long this is. It takes about 25 days for the sun to go all the way around. So that's what it looks like if you were to just look at it. This is what the magnetogram looks like. Here you can see it going. You see the activity. You can see the magnetic field evolving as it goes. You can't really see it in that one, but you can see it in this one. But wait. Oh, but wait. This is a higher energy waveband. This is the 171 angstrom waveband. This measures higher energy stuff, hotter stuff. So they say that this one targets 171 is 600,000 Kelvin gas. So this is pretty hot, not crazy hot. 600,000 degrees is only a little hot. But here you can see a lot more activity. You see how crazy all these things are going. And you can see the structures of the stuff on the field line that's on top of the sun. And you can see all of the reconnection. And I'll talk about reconnection in a second. Actually, it is time to go, so I'm not going to talk about reconnection. Here's another one. You can see the magnetic activity a lot better. I think you can see it best in this one. And then here is the corona. So this one measures the corona. So you can see how hot all this crap is. This is what we're looking at, is this stuff here. And you can see over where the stuff is, the corona's hotter. Up there where there's not as much magnetic activity, there's not nearly as much corona. Because these magnetic fields are what's heating up the corona. It was not well understood for a long time how you have a 6,000 object underneath million-degree gas. But now we feel like we understand that pretty well. Okay, does anybody have any questions about waves or buoyancy or sunspots? Everybody good? All right. I think that's it for me for today. I will see you guys on Tuesday. So there's a reading due. Read it fast. I'm not going to cover much of that stuff. The only thing I really want you to pay attention to is reconnection. But read the rest of it because it's cool. And then there's another reading due on dynamos, and I'm probably going to spend most of I'm going to do reconnection really fast, and then I'm going to do dynamos for the most of Tuesday and then the following Tuesday. And then we're done. And then it's Christmas time. Merry Christmas.